Today we will study singular solutions of Kadamtsov-Petriashvili equation and derive equations of motion for poles. The KP equation is as follows. And it is easy to see by substituting in this equation and extracting the most singular terms that if the function u has a pole at some point a, this pole must be of the second order with coefficients -2. And A is, now if we consider solutions with many poles, then we should write something like this. And the poles depend on y and t. It turns out that this ansatz is compatible with the equation. So if we substitute this into the equation, we will see that the number of poles is the same. When we change y and t, the number of poles is the same, and all what happens is some motion of these poles as functions of y and t. And our task is to obtain equations of motion for these poles. And we will see that these equations of motion are nothing else than a Calogero-Moser system. However, when you substitute this ansatz into the equation, it is a very complicated problem to derive the equations of motion for poles. And in fact, the variables y and t separate. And this is not so easy to see from the equation after the substitution. And Krichever suggested a method that allows one to avoid this difficulty and separate the variables from the very beginning. And now I will show how this method works. For this, we should recall that the KP equation is a compatibility condition for two linear problems for some function psi of x, y, and t, and an additional complex variable z, which is called spectral parameter. And the two equations are like this. The first is equation of this form. second order equation, and another one, not t, y. And another one is equation for derivative by t, and here we have some third order operator, which we don't need at the moment. And if you require compatibility of this system, so this means that there is a large family of solutions, common solutions to these equations, which depend on this additional parameter z. This z does not enter explicitly in the equations, but the solutions depend on it. And what we should do to consider dynamics of poles with respect to y is to substitute the corresponding ansatz into this linear equation. So u here is of this form with poles of second order, and it is not so difficult to see that the ansatz for psi compatible with this ansatz for u is can be taken in the following form. This is the usual exponential factor, and psi must have poles of the first order in the same points xi for the equation, for this equation to be compatible. So we can write with some coefficients. We fix t, for example, fix it to 0, and consider the case when only y changed. And so these coefficients may depend on y and z, but not on x. All dependence on x is this. It is a rational function. And C naught is some arbitrary constant coefficient which can be taken, for example, equal to 1, because psi is defined up to multiplication by a common constant factor. So we should substitute this ansatz, this and this, to the first linear equation. You obtain, let me bring everything to the left-hand side. When you substitute this and this into this equation, you get, on the left-hand side, you get some rational function of x, say r of x. This function is equal to 0 at infinity, and may have poles at the points xi up to the third order, because when we differentiate twice this psi, we get pole of the third order. However, it is easy to see that the poles of third order cancel identically. They originate from this term and from this term, and they cancel in this combination. So the remaining poles are second order poles and first order poles. And to obtain 0, we should require that the coefficients in front of these poles in this expression are 0. Then we get an identity. These conditions lead to the following system of equations for the coefficients Ci. The coefficient at the second order pole becomes 0 if the following condition is satisfied. X dot is derivative with respect to y. Now, y plays the role of time. And the first order poles cancel if the following equation is satisfied. And this
any dependence on time or not?
dot means y.
But
Deri
is there time anywhere?
time is fixed in these equations. Now, y plays the role of time.
But we have time in x, x with indexes, yes. In poles.
X poles xi depend on y and t. But we fix t and consider the dependence on y. So this is our time. This system, it is a linear system. Oh, sorry. Here is Ci. A linear system for coefficients Ci. N equations here and n equations here. But there are n coefficients and we have 2n equations for them. The system is overdetermined. So we should require compatibility. To do this, we first rewrite it in a matrix form. Where C is the vector with components Ci, and E is the column vector whose components are all equal to 1. This is the first system, and the second system can be written in this form, where L and M are the following matrices. Of course, you recognize here the L and M matrices for the Calogero-Moser system with the coupling constant equal to 1. And compatibility of this system is just the Lux equation. To see this, let us put C naught equal to 1 and differentiate the first equation with respect to, not t, this is y, with respect to y. We get the following. L dot C plus L C dot is equal to 0. I forgot here this term because we differentiate, so this is minus z times c dot. Now we substitute here c dot from this equation and obtain the following. And here we replace what should we do? We should write it in this form. This term. And substitute here this z times c from this equation. And this is L times c minus e. Then we get the following, minus m L and everything x to the vector c. So compatibility means that this equation is satisfied for some family that it has not just a single solution for C, but some solution which covers all the space of this vector. So this means that this operator must be 0. And this is nothing else than the Lux equation. So we have proved that the poles as functions of y move as Calogero-Moser particles for rational Moser model. And the function psi for this solution can be written in the following form. You see that this function is symmetric, more or less symmetric with respect to permutation of x and z. In the both variables, it is a rational function with simple poles. And this reflects the self-duality property of this rational Calogero-Moser system. Now let us turn to elliptic solutions. For elliptic solutions, we should make the following ansatz for U. It is a sum of Weierstrass P functions, and in general plus some constant. So as you remember, this function has a first order or second order pole at xi with zero residue. So this is around this point, this pole, it has the form of second order pole with coefficients -2. So we should solve the linear problem. Now the coefficient u in this equation is double periodic function of x. And it is natural to find solutions among double Bloch functions. Double Bloch function means that when we shift by period, this function acquires some constant multiplier, which is called Bloch multiplier. And double Bloch means that it is a Bloch function with respect to both periods. Here alpha is 1 or 2. The simplest double block function is exponential function. Just e to the ax with some constant a. When we shift x by periods, it acquires some multipliers. But this is a rather trivial double block function. Every non-trivial double block function must have poles in the fundamental domain. And the simplest case is when this function has only one pole. And an example of this function is this Lamé-Hermite function, which is sigma of x plus lambda, sigma of lambda, sigma of x times exponent of minus z of lambda times x. This function has just one pole at 0 in the fundamental domain. And it is easy to see that it is indeed a double block function. And the block multipliers for it are exponents of 2 zeta of omega alpha lambda minus zeta of lambda omega alpha. We should note that the transformation of this form sends a double block function into another double block function with different block multipliers. And the two block functions which are connected by this transformation, by multiplication by some exponent, are called equivalent. So any double block function which is not equivalent to the exponential function must have poles. And in general case, when we have n poles here, we can take the following ansatz for the psi function. So this is a linear combination of this simplest double block functions with only one pole at the point xi. So this expression is an elliptic analog of the representation of a rational function as a linear combination of simple poles. So we have this, and this function is also a double block with block multipliers. the function psi tilde, which is also a double Bloch function. If we choose these coefficients so that the right-hand side does not have poles, then it must be equal to exponential function, the trivial double Bloch function. But this function, defined in this way, has a pair of double Bloch multipliers which are not equivalent to the Bloch multipliers of this exponential function. So this means that this constant must be 0, so this equation is satisfied identically. So we should substitute this and this into this equation and cancel all poles. Again, there are poles of third, second, and first orders. The poles of the third order cancel identically. And the requirement of cancellation of other poles look as follows. For simplicity, I will not write here the second argument. Again, this system is overdetermined. And we can write it in a matrix form. With matrices L and M, and now they depend on lambda. So you, again, you recognize here the Lux pair for elliptic Calogero-Moser model, and the compatibility of this system is the Lux equation. So we conclude that the poles move as Calogero-Moser particles of elliptic Calogero-Moser model. The problem for you is to repeat, not just repeat, but generalize these calculations for the third, for dependence on t. In this calculation, t was fixed in KP equation. We considered the dependence on y, but now let us fix y and consider the dependence on t. The calculation is more difficult, longer. There are more poles of higher order, but everything can be done, and as a result, you should obtain the Calogero-Moser dynamics with respect to the third Hamiltonian flow. I mean, the flow with the Hamiltonian given as a trace of third power of the Lux matrix. Let me write it explicitly. Now we turn to the general Kadamtsev-Petveashvili hierarchy as a infinite number of compatible equations for infinite number of independent variables with infinite number of dependent variables. The KP hierarchy can be introduced using pseudo-differential operators. A pseudo-differential operator is a formal expression of the following form. Where v, k are some functions of x, and this operator, differential operator, has the standard commutation relation with any function. Multiplying both sides by inverse power of the differential operator, we can read this relation as the rule how to move this inverse power of differentiation to the right, from left to right. And this is represented by a series, infinite series. So this operator is a kind of Laurent series, non-commutative Laurent series. The number n is called the order of this operator. So it starts from some positive or negative power of dx, and the series goes in inverse powers. So this is like here. And in general, infinite series. These operators can be, say, this is Q1, and Q2 of a similar form, and they can be multiplied as Laurent series with taking into account that this symbol does not commute with the coefficients. There is a commutation rule, this or this. A few problems. To prove the following identities. G is some any function. F is another function. This is the binomial coefficient. if n is positive. The binomial coefficient is if we have a pseudo-differential operator of this form, we can define its positive and negative parts. So this positive part is projection to non-negative powers of dx. So it is a differential operator. And Q minus is the rest. It consists in negative powers of dx.
Can you please explain how the equation, the second equation, was obtained?
Which one?
Like what partial derivative in the power of -1 yeah.
This?
Yeah.
Let us do this in some detail. So multiply. This you understand. Multiply. Then we obtain f is equal to f prime dx to the -1 plus
we need to act by the negative derivative from the both sides. So in the left side f with partial derivative. We need to simultaneously act from the both sides.
so something that may be wrong here. Multiply from the right first. And then from the left. Rewrite it in this form. You agree? And now apply the same procedure to this. And if you do this many times, you get a series. Now, let me introduce the KP hierarchy in the Sato form, in the form of Lax representation. Let us consider a pseudo-differential operator of the following form. Plus, in general, infinite series, where u1, u2, and so on are some functions of x. Let us introduce evolution in the space of such operators in times t1, t2, t3, and so on. To impose the Lax equations. So we should raise this operator in mth power and take a differential part. These differential operators, let us choose a separate notation for them, AM. The AM is a differential operator of degree m. For example, let us consider this equation for m equals 1. Then we get differentiation this. We should differentiate coefficients, and we obtain that d over t1 of uj is equal to this operator is just a1 is just the derivative. So taking commutator, we get derivatives of this coefficient. So we see that the vector field d over t1 is the same as the vector field dx. So the variable t1 can be identified with x plus some constant. For example, a2 is dx squared plus 2u1, and a3 and so on. The compatibility of the Lax equations can be expressed in the form of the so-called Zakharov-Shabat equations. Which are more convenient to define the hierarchy as differential equations in finite number of variables for a finite number of functions, because what you get from here, you get infinite number of coupled equations in infinitely many variables and for infinitely many functions. And the Zakharov-Shabat equations are of this form. they just mean that this commutator is 0. In fact, the two formulations of the KP hierarchy in the Lux form and in the Zakharov-Shabat form are equivalent. I will not give the proof how to obtain Zakharov-Shabat equations from the Lux equations. You can find it in the lecture notes. It is a rather technical calculation, so I will not explain it now. Each equation for any given m and n is equation for m plus n functions as functions of tm, tn, and x. So each equation here is a system for m plus n functions, and the partial differential equation contains 3 variables. For example, the first non-trivial case is m equals 2, n equals 3. In this case, you get the, if you calculate the left-hand side, you impose the condition that coefficients in front of all differential operators here is 0, you get the Kadamtsov-Petriashvili equation for the function 2u1. Originally, here you have u1 and u2 in this case, but u2 can be excluded, and you get a single equation for 2u1. And this is the Kadamtsov-Petriashvili equation. The Zakharov-Shabat equations are compatibility conditions for the linear problems for a function psi. And psi is of this form. It is convenient to introduce the generating function for the times. And then here we have, in general, infinite Laurent series in negative powers of z with some coefficients which depend on time. In the full theory, one also introduces a dual, and this function is called wave function or Baker-Hieser function. the term Baker-Hieser function comes from solutions associated with Riemann surfaces, quasi-periodic solutions which are constructed from algebraic curves or Riemann surfaces. And in this case, this function becomes a well-defined function on the Riemann surface, which is called Baker-Hieser function. For general solutions, it is called rather wave function. And it is convenient to introduce dual wave function, which is given by a similar series, but here we have e to the minus psi, and again some series with different coefficients. And this function satisfies conjugated differential equations. Where this operation means the following. And for any two operators, we have this. It can be shown that the all infinite set of linear problems is equivalent to the following integral equation. Where by t I mean the infinite set of times. And the sets t and t prime are arbitrary. The contour is a big circle around infinity. I will not give a proof. It can be found in the works by Kyoto School, Jimbo, Miwa, and their collaborators. The proof is rather technical. And another important statement is that from this, it follows that there exists a function tau, a function of all infinite set of variables, which is called tau function. And from this condition, it follows that the wave functions can be written in the following form through this tau function. Where this notation means that we should shift the times in the following way. This is psi and psi star. Again, I will not give the proof because it's rather long. You can find it in the original papers. And this function, tau function, is a very important fundamental object for the theory of not only for the KP theory, but for tau function can be defined for all integrable hierarchies, KP, Toda, and their multi-component analogues. In terms of the tau function, this equation acquires the following form. And it is called the generating integral bilinear equation for the tau function. Choosing t minus t prime in some special way, you can obtain from it many equations for the tau function. For example, if you choose this in this form, where A and B are some complex numbers, then this exponent becomes you substitute this here and get the some say sum over k this is expansion of logarithm, so we can write it in this way. So this, in this case, it becomes so here you get and better to introduce a third parameter and write it in this way. And then you can calculate the integral by residues at these points. There are 3 poles, simple poles, and you should take residues, and then you get equation of the following form. This equation was first obtained by Miwa, and it can be proved that this equation is already equivalent to the following hierarchy. So from this equation, this general relation already follows. The coefficients of the Lax operator can be expressed through the tau function. For example, this is u1 and u2. And we will need another corollary of this equation, which is obtained after differentiating it with respect to Tm and putting T prime equal to T after that. In this way, you get the following relation. Better to keep dependence on x here. Okay, this is probably all for today, and next time we will consider we'll obtain the result first proved by Shiota in 1994. It established the equivalence of, or rather correspondence of KP with Calogero-Moser hierarchy on the level of hierarchy and hierarchies. And it will be shown that the evolution, the Hamiltonian flow HM, one of the higher Hamiltonian flows in Calogero-Moser, this dynamics is equivalent, is the same as dynamics of poles of KP solutions with respect to time Tm. So this is, we showed it for m equals 2, and this result was obtained by Krejciever. A problem for you is to prove it for m equals 3 and for elliptic solutions. And next time we derive this for the general, for any m, obtain this statement for rational solutions. More recently, it was proved, this result was generalized to trigonometric and elliptic solutions, and but the formulation is more complicated. I will show it next time.